So in this example problem here, we're asked to determine the total strain energy within the beam due to the applied force. All right. So in this case, we have a simply supported beam. So we have a pin at point A, and we have a roller at point B here. Okay. So for both of these, we're going to have We're going to have a reaction force along the y direction, right, and a reaction force along the y direction here. We do also have a reaction along the x here, but there's no applied force in the x direction, so we can just set that equal to 0. Okay. So using statics, we can solve for RA and RB using our equilibrium equations. So if we sum all of our forces along the y direction and set that equal to 0, we would get RA plus RB would be minus 12 kilonewtons is equal to 0. So we can say that the sum of RA plus RB must equal the applied force of 12 kilonewtons. And then we can say that if we take the moment about point A and we set that, and we sum all the moments about it, and we set that equal to 0, we know that we would get a moment of minus 12 kilonewtons times 0.5 meters, and then we plus RB times 1.5 meters. Alright, so if we rearrange all these terms, alright, we get R of B would be equal to 12 kilonewtons times 0.5 meters would be equal to 6 kilonewton meters divided by 1.5 meters. So we'd end up getting RB would be equal to 4 kilonewtons. Alright, if we plug in 4 kilonewtons into this equation here, we'd end up getting that RA would be equal to 8 kilonewtons. Okay, so we have our two values of RA and RB. Okay, so once we have those, we're going to calculate our shear force V of x and our moment M of x as a function of the beam. So to do that, we're going to draw our shear moment diagrams. Alright, so hopefully you remember this from your strength of materials course. So we have our shear force as a function of x here. So if we look at our, as we go across the beam here, alright, at R we will have our initial force RA, alright, which is equal to 8 kilonewtons. Okay. Then we will have our, we go for 0.5 meters. There's no transverse loads applied to the system, so we're still at 8 kilonewtons. Then we have our applied load of 12 kilonewtons at 0.5 meters. Alright, and then so we're left with negative 4 kilonewtons here, all the way until we get to RB, where we then have our 4 kilonewton load back to 0 here. Okay, so we can then, for the moment equation, alright, so for our moment equation, what we can do is we can integrate our shear diagram, so we know that the moment of x is equal to the integral of v of x dx. So if we integrate our shear diagram, we should be able to get our moment. So we have a constant 8 kilonewtons here, so we know that our moment is going to be an integral of a constant with respect to x would just be equal to that constant times x. So we would get a slope of 8 kilonewtons times x. And then at this point here, we would have, we integrate across the rest of the length, and we would get a slope of minus 4 kilonewtons times x, and then we have to take into account the intercept if we extended this line all the way out. So what we can do is we can say it'd be minus 4 kilonewtons times x minus 0.5 meters times plus whatever the value is at this point. So if we plug in 8 kilonewtons times x, and x is equal to 0.5, that would be equal to 4 kilonewtons. Alright. Alright, so really quick, just to check our work, if we plug in x is equal to 1.5, we should get the moment should be equal to 0 at that point. So if we plug in x is equal to 0.5, we get minus 4 kilonewtons times 1.5 minus 1.0 meters plus 4 kilonewtons. So we end up getting, should be 1.5 minus 0.5 meters. We plug all that in, we get minus 4 kilonewton meters plus 4 kilonewton meters, which is 0. Alright, so that's good. Alright, our equations work out. So we can just write these two terms as piecewise functions. Alright, so if we do that really quick, we're going to write v of x and m of x as piecewise functions. So I'm going to just pause the video here and write out those piecewise functions. Alright, so now we have our two functions v of x and m of x as a function of x. This is great because our two equations for our bending stress and our shear and our bending strain, our bending strain energy and our transverse strain energy both require v of x and m of x. All right, so let's first do the bending stress, our bending strain energy, UB. We know that U of B is equal to 1 over 2e to the iz from earlier in the lecture. If we integrate from 0 to L, we know it's equal to, this is the definition of our bending stress here. All right, so we can calculate, if we plug in for this integral here, we end up getting 1 over 2e to the iz, alright, times the integral from 0 to 0.5 meters. We plug in our v of x term, which we know is just equal to 8,000 newtons squared times dx. Alright, and then we have to do the rest of the integral across the whole length. So we're going to go from 0.5 meters to 1.5 meters, where we know that the shear as a function of x is going to be equal to, this should not be 8,000, this should be m of x, not v of x, so it should be 8,000 newtons times x, and then for the second term it's going to be equal to minus 4,000 Newton, it's going to be equal to minus 4,000 newtons times x plus 6 kilonewton meters squared times dx. Alright, so that is our total equation. If we integrated, if we squared both of these terms and we integrated them across their bounds and we did some algebra, what we end up getting, and we plugged in the initial information from the problem statement that we were given. So we were given the elastic modulus, we were given the Poisson's ratio, and we were given the cross-sectional area here, so we could calculate the polar moment of inertia, the moment of inertia that way. We do all of that, plug it all in. What we ended up getting for our bending stress is 74.93 newtons per meter. Okay. So we can repeat this process for the shear energy on our system. So we can say, what is our shear energy on our system? We know it's going to be equal to this equation here, 1 plus the Poisson's ratio divided by the elastic modulus times the area times our shear correction factor K. and then we have to integrate that from 0 to L times v of y squared dx. Okay, so all these terms out front here are constant terms. Our k term is our shear correction factor for a square cross section like we have in this problem. K is equal to 1.2. We can just look that up from this table here. Alright, so we had a rectangular cross section, therefore our K value should be 1.2. Alright, so if we then our integral here, we're just going to use our V of our shear force equation as a function of x. So again, that changes in two spots, so we're going to integrate from 0 to 0.5 meters, and along that path it's going to be equal to 8,000 newtons squared dx, plus if we integrate from 0.5 meters to 1.5 meters, we would have the shear force along that region is minus 4,000 newtons squared dx. Alright, so after we do those integrals and plug in all of our values, our value of our shear stress, our strain energy due to the shear force would be equal to 0.292 Newton meters. Okay, we can calculate our total strain energy as the sum of UB plus US. If we calculate that, it's equal to 75.2 Newton meters. Okay, so from this example problem, you can see that U of B is typically much greater than U of S. So often, in many problems, you'll be asked to just ignore U of S, the contribution of U of S to the total strain energy. So you would sometimes you'll assume that U of T is approximately equal to U of B because since U of S is so small. Okay, so in conclusion, what you have to do for these types of problems, if you're asked to find the total strain energy within a system, is you have to use in this case we use statics to determine functions of x for v of x and m of x, which we defined here. Once we had v of x and m of x, all we had to do was just plug them into our two integrals to solve for the total strain energy along the beam U of B, and to solve for the total strain energy due to the shear stress, which was here. Alright, so we plugged in all those values, evaluated these integrals, and plugged in the given information, and we were able to calculate our total strain energy.